Hello calculus students. In this problem we're going to do a full analysis of this function here, x over x squared minus 4. And when I say analysis, what I mean by that is we're going to look for intervals of increase, decrease, we're going to look for critical points, inflection points, intervals of concavity, as well as horizontal and vertical asymptotes. Okay, I'll give a full summary at the end of this video, giving you the full scale analysis of this function, as well as a plot of the function. So remember that the first thing we're going to do when we're looking to determine intervals of increase and decrease is we're going to take the first derivative, which you can see that I've done all the work here for the first derivative. So we take the derivative of the top, which is 1, the bottom left alone, minus the top left alone times the derivative of the bottom over the bottom squared. So that's the quotient rule. And then I'm going to do a simple simplification here, algebra. So 1 times x squared minus 4 minus x times 2x, which is minus 2x squared. Then I'm going to rearrange the terms. I'm going to take this 2x squared and bring it over here. The minus 4 going to leave there. And then x squared minus 2x squared is minus x squared minus 4. And then this minus sign here and this minus sign here, just going to factor that out and put that here. So then we have x squared plus 4. And this is what our first derivative looks like. Okay. Then, now that I have f primed, I'm going to compute f double primed. And once again, I'm going to use the quotient rule, and here I kind of spell it out for you because I'm going to have to use a chain rule here, so I wanted to do this a little more slowly. The minus sign that you see here, I'm just going to put that in front of the whole fraction, and I'm going to take the derivative of x squared plus 4, the bottom left alone, the top left alone now, and the derivative of the bottom, which we're going to have to use a chain rule to do. Then we have the bottom, which is something that's already squared. We're going to have to square it again. So we compute this derivative here, and we get 2x. This guy is left alone, minus this one, which is just x squared plus 4. Now, here we have to use the chain rule. So the 2 is going to come down. Subtract 1 from the exponent, we just get a 1 there. And then we have to take the derivative of the inside, and that is 2x. And then this x squared minus 4 squared, when we square it again, we get a 4th power. Now we're going to clean up this numerator that you see here. Okay, what I'm going to do here is I'm going to factor out the greatest common factor, and that would actually just be the x squared minus 4 and one of these x squared minus 4s. So when I factor out the x squared minus 4, I get out in front here. The only thing that's left here is a 2x and one of these x squared minus 4s. Minus, and then I have 2 times 2x, which is 4x, and this x squared minus 4, because this guy got factored out over here. Then I'm going to simplify a little bit. I'm going to break this up into x squared minus 4 times x squared minus 4 to the 3rd power, because that's to the 1st power, that's to the 3rd power, that gives me to the 4th power. These will cancel, and now we're left with this expression. And in the next slide, I'm going to clean this up a little bit. So I'm going to collect these like terms here and here, and I'm going to collect this term and this term. So we collect like terms. 2x cubed minus 4x cubed gives me minus 2x cubed. Minus 8x minus 16x gives me minus 24x. Then the next step is I'm going to factor out the greatest common factor from here, which would be a minus 2x. So I factor that minus 2x out. There I have highlighted the minus sign. And I'm left with an x squared plus 12. You could double check that by saying minus 2x times x squared is minus 2x cubed. Minus 2x times 12x is minus 24x. So that's just checking my work. Then I'm going to take these minus sign times this minus sign, and I'm going to get a positive. And here is the second derivative. So let's do the sign analysis on this second derivative to get the intervals of concavity. Alright, so we have a 2x and an x squared plus 12 and an x squared minus 4 to the third power. Alright, what I did was I look here and I see I get vertical asymptotes at plus or minus 2 because that's what's going to make the denominator 0. So I put a minus 2 and I put a plus 2. And the other point is what's going to make the second derivative 0, and that's where 2x is 0, and that's at 0. This term is never 0 because this is always positive, x squared is always positive, and 12 is always positive. So when I do my sign analysis, I'm essentially going to ignore this term because I know it's always going to be positive. Alright, so what I did was now I chose a test point, minus 3, which is to the left of minus 2. And I see that I'm going to get a positive number over a positive number, and then I'm multiplying that by a negative number. So that means we're going to get a negative. Then I pick a test point between minus 2 and 0. I picked minus 1 here. And so I have a positive, and then 1 minus 4 is minus 3 to the third power, which is still negative. So I have a negative over negative, and that gives me a positive. And now I'm going to use a test point between 0 and 2, so I'm going to pick 1. And if I plug in 1 for 2x, I get a 2 times a positive number, and then 1 minus 4 is a negative. 1 minus 4 is a negative number, and a negative to the third power will be a negative. So I have positive over negative, and that is going to be negative. And then I need to pick a point bigger than 2, so I'm going to choose 3, and 2 times 3 is 6. And then I have 9 plus 12, so I have positive, positive, and then over positive. So that means I am going to have a positive here. So my intervals of concavity, I see that we're concave down, concave up, concave down, and concave up. All right, let's go to the summary. So it may seem like I've ignored what's happening with this first derivative, but it's actually easy to do the sign analysis there. So I saved it to the end. It's never increasing, so I put down that there's no interval of increase, and you can actually see that. X squared is positive, 4 is positive, so x squared plus 4 is certainly positive. This quantity is being squared, so it is positive. So you have a positive over positive, which gives us this whole expression here is positive, but then we're multiplying it by a negative. So that means f prime of x is less than 0 for all x. And so that means that f is decreasing from minus infinity to positive infinity. And then the second derivative here, we did the sign analysis for that, and you may recall that we were concave up from minus 2 to 0, union 2 to infinity, and we were concave down from minus infinity to minus 2, union 0 to 2. And looked at the asymptotes. Now remember, what makes the denominator 0? That'd be plus or minus 2. And you can see the vertical asymptotes by letting x go to minus 2 from the left, x go to minus 2 from the right. And we see that this function here is going to minus infinity. And I can determine that by looking at test points. You can look at, for example, minus 3 and put it in there. And you'll see that you get a negative number. Similarly, x over x squared minus 4, I look at minus 2 from the right and I get a positive infinity as I evaluate that limit. Similarly, we look at 2 from the left. If we plug in numbers like 1, we get a positive over a negative, so that'd be negative infinity. And if we look at x approaches 2 from the right, we can use a test point like 3, and we get positive over positive, and that would give us positive infinity. So this is what the vertical asymptote analysis looks like. I'll talk about this horizontal asymptote analysis in the next slide. Okay, so increasing none, decreasing over the whole real line, concave up where we said it was going to be, and so now you can see we are concave up from minus 2 to 0, and we're concave up from 2 to infinity. That's on this side. We are concave down from minus infinity to minus 2, and we are concave down from 0 to 2. Here are our vertical asymptotes. That was this analysis here. And then if we take the limit as x goes to infinity, that's how we determine the horizontal asymptote. And you see that the denominator is the dominant term. The x squared dominates the x. So as we let x get very large, the denominator is going to dominate, and we will get 0. And so y equals 0 is our horizontal asymptote. And this is the summary of our analysis here, and it comes alive here in the plot. Okay, good luck.